Welcome to our show. I'm Todd Haugen with News Director Larissa Donovan. And joining us in our studio again today to talk about weather and climate, this time retired BSU geography professor Dr. Charlie Parson. Charlie, welcome back.
Good morning. Happy to be here.
Well, glad you could come in and share some of your knowledge, the material that you gained from years of study in this area and teaching at BSU. How many years did you teach?
28 years at BSU, 2 years before that at SUNY Buffalo, and graduate school at the University of Iowa.
And you did a terrific job, I must say, having been in some of your classes myself.
Thank you.
Charlie, weather and climate are something that are frequently discussed. I mean, every single day we talk about weather. Climate is certainly in the news of late. And what's the difference between the two?
Well, I like the phrase that climate is what you expect, weather is what you get. Climate's the summation. Typically, a formal professional climatologist says 30 years of data to make any climatic statements. And then in the last century, if you want to call it 2000, but the determination was that which 30 years makes a difference too. And so for the first part of my career, it was all based on a Department of Agriculture study that started about 1910 and ended about 1940. And they published these summations of the national climate. Then we had a few weird years in the 50s. And when you added the next 30 years in, things shifted some. And that was when I realized, well, maybe it depends which 30 years.
Mm-hmm. Even in this relatively short amount of data keeping in terms of the history of the Earth, there have been some dramatic changes in our weather patterns.
Oh, absolutely. And in the basic data of the climate, of the measurements of the Earth. Now, we have measurements of the Earth's climate that go back millions of years. This was something I was involved with in New York, is ice cores. And in the Arctic and Antarctic ice cores, Greenland ice cores, Antarctic ice cores, you can measure global temperatures all the way back to 2-3 million years.
And see, how do you do that from ice cores?
There's an oxygen isotope pair, oxygen 16, oxygen 18, and the ratio of 16 to 18 is dependent on temperature. And so when you have ice that's 1,000 feet down in an ice core, you can count the years just like counting tree rings. And then you analyze the ratio between oxygen 16 and oxygen 18, and you get a temperature.
And are there pretty complete samples of these isotopes and this air over the course of all that time?
Very.
Okay, so you see the patterns of glaciation?
Yep, absolutely. You see the about 100,000 year cycle that we have typically on continental glaciations in the last couple million years. The glaciations, it's weird because we have had our glaciation that most recently covered Minnesota, and then 3 continental glaciations before that. And then you have to go back millions of years to the Permian period to find a previous glaciation. And the thought is that it takes continental drift in order to close the Bering Sea, to create the ice at the north that leads to the snow staying on the land that leads to glaciation. So it's not just the Earth-Sun relationships. That triggers a 100,000 year cycle. It's called the Milankovitch Cycle. And that cycle's always been there. But the continental orientation with continental drift probably is the dependent factor on whether or not you get glaciations.
Not some sort of extraneous event, not some sort of meteor strike, not mass eruptions for whatever reason.
There's a pretty distinct cycle, and it's based on the variation in the tilt of the sun, the variation in the distance that we are from the sun. That varies from 91.5 million to 94.5 million, and you and I learned 93 million.
Right.
Well, how about if you're tilted as much toward the sun as you can be, and that varies in maybe a 20,000 year cycle, and you're 91.5 million miles from the sun, which would make it as warm as it could be. And then there's a third variable in there that can also be maximized. And if all 3 of those converge, you get a very warm period. And if all three of them diverge so that you're faced away from the sun, you're as distant from the sun as you can be, and your periodicity is such that you're furthest from the sun in our winter, then you get a really nasty winter and you get glaciations, because that lasts for thousands of years that we're in that stage in our rotation.
Why does it vary?
Well, the ellipse that we all know that we go around the sun in an ellipse, not a perfect circle. And that ellipse, think of it as an egg lying on its side, and that egg itself rotates. So we're at different distances as the ellipse itself moves around. And that's the big one. The crazy thing to me is a mathematician, climatologist named Milankovitch worked this all out early in the 20th century with paper and pencil. Years and years and years of calculations. And it wasn't until about the 1990s that it was run with our best computers of the era, and they found his work was correct. Checked his work. Oh my gosh, he's right.
How could he do that? By hand?
Oh my God. It was just amazing. Just amazing.
So we learned in your class called Weather and Climate that we're closest to the sun in January.
Right, January 8th,
farthest
typically.
In June.
Yep.
Aphelion and perihelion.
Very good. Very good.
Wow,
Todd. I'm going to go back and change your grade.
A little bit. It could use some help. In any event, though, if that point is shifting a little bit year to year, and we're perhaps at a different part of our orbit about the sun, I mean, do we know that the sun is uniform in its amount of radiation that it's sending out, depending on what side we're on of it when we're closest or farthest away?
Well, again, given that climatic sense of 30 years or so, yeah, the sun isn't varying much. You know, the sun will go out in a few billion years, maybe trillion years. But for now, from year to year, century to century, it really doesn't vary a great deal.
Okay.
Not enough to change climate.
So climate, of course, is, I can't imagine who wouldn't have heard of the current concerns about our climate. Were we already in a part of our climatological cycle that would have called for us to be warming up?
Not anywhere near the rate at which change is taking place now. We are between glaciations. We're not headed into another glaciation according to the Milankovitch cycles, but we're not anywhere near as warm as the Milankovitch system would cause us to be. So we are in a time when we would be warming, but we're way out of that realm. You know, I have a grandson who's 8 years old. He's 5'1". He weighs 117 pounds, and he's not on any of the pediatric growth charts. He's just off the charts, and our heating right now is off the charts as far as what would happen if we were in climatic balance, if you will.
Is it primarily the additional carbon dioxide in the atmosphere that's causing it? Appears to be. A factoid I stumbled onto, where was I? I can't even remember. Giacomo Beltrami came up here and discovered the headwaters of the Mississippi at Lake Julia. Well, a little debatable. Yeah. But this was 1823, and the way he got here was a steamboat. And in climatology, we look at the current increase in global temperatures and carbon dioxide rising, typically starting around 1825.
Around the time of the Industrial Revolution, correct?
The advent of steam.
Yeah.
Really, it's the advent of steam, but that he had a steamboat to bring him up here in 1823. I was just kind of stunned. I thought, God, when did that start? Well, it turned out it started in the 1780s that we had our very first steamboat. And that was a big deal. Mm-hmm. Then we went to steam locomotives. Then we went to steam-driven factories all over the place.
New York City is still run by steam.
Well, yeah.
Parts of it, yeah.
So is Boston, you know. Steam generated by Bemidji's garbage warms Boston. But this increase in carbon dioxide started about then, and it absolutely hasn't gone down. Another odd one to me is that when we have volcanic eruptions, that emits a huge amount of carbon dioxide. But it also emits a huge amount of dust that gets into the stratosphere, the higher layer of our atmosphere, and that actually causes global cooling. And so volcanic eruptions that put out extra carbon dioxide actually reduce the temperature of the Earth. And that's pretty well documented. We have a couple of years that were called years with no summer, and they were related to volcanic eruptions. And on the overall trend of carbon dioxide, it just keeps going up, and those volcanic eruptions don't even make a blip in that curve because human production is so much greater than volcanic eruptions.
We could go for a good few hours with this show. But why, for those that have never heard, why carbon dioxide is a culprit in global warming? What's the problem?
It's really neat. If you have sunshine coming down through the Earth's atmosphere, it's in the range that we call visible light. And in the visible light, our Earth's atmosphere is transparent. So all the visible light comes straight on down to the ground on a clear day. And in parts of the world that are perpetually clear, like Sahara Desert, it's always coming down. But when it warms the surface and heats the surface, and the surface radiates heat back into the atmosphere, that's long wave or infrared radiation. And our atmosphere is actually frequently opaque to infrared. None of it gets out. If we have a lot of atmospheric moisture, if we have a lot of carbon dioxide, none of it gets out.
That's what we call the greenhouse effect?
That's the greenhouse effect. That's the overnight. We don't get to freeze every day. On the moon at night, if you will, the temperature is about 5 degrees above absolute zero because there's nothing to hold any of that radiation in. Whereas here, in humid areas, we hold in most of it. In the Sahara, it all goes out at night. And you've heard about people freezing in the desert at night, whereas that wouldn't happen here because we have so much atmospheric moisture. But carbon dioxide fills 2 parts of that outgoing spectrum that moisture doesn't fill as well. And so the higher carbon dioxide is, the less heat can get out in the spectrum parts that carbon dioxide is absorbent in. So as we increase carbon dioxide, we increase retention of heat.
Plants consume carbon dioxide.
Sure.
But
and
we
they give off carbon dioxide.
We don't have enough to evidently take care of the problem.
Well, they're part of the absorption system. The ocean is part of the absorption system. But I view it this way, that the Earth has balanced out over millions of years to have a relatively stable temperature regimen where we can really see things like this Milankovitch cycle happening. But it's a delicate balance. In 1964, when I started college, 1967, I took my first meteorology course. Carbon dioxide was 33 parts per million. And that was taught like, this is gospel, this is what it is. But if you went back to 1825, you found that it was about 28 parts per million. So between 1825 and 1967, it had increased 8 parts per million.
Which is a lot. It doesn't sound like much, but it is.
Well, it's better to think of it as a ratio. Well, it's 8 parts out of 24 parts. That would be 25%. So carbon dioxide during that time had increased about a third. But since I graduated, 1930, the 33 parts per million has gone up to above 40 parts per million. So we've had an increase of 25% just since I took my first meteorology course. That's drastic. It's just, and if this Earth is balanced, then the Earth is in the process of compensating for that change, and the way it's compensating is it's increasing its temperature because the carbon dioxide keeps infrared from getting out.
And will it thereby increase the amount of plant life? And is it trying to increase its amount of consumers of carbon dioxide?
Well, it's interesting. There is data, and it's been promulgated by some of the pseudoscientists that if you increase carbon dioxide, you increase food production. In fact, that will work in a greenhouse, but you have to increase carbon dioxide levels up to about 60 parts per million which would sort of end life as we know it, in order to have that happen. So the small parts of increases in carbon dioxide, they're not going to be linked to increases in growth and production. Only in a lab situation in a greenhouse carefully controlled can you make that happen. And we hope that doesn't happen, because if it does, we're going to look at 20-degree increases in global temperatures.
What should, really, we're out of time for our show. We're going to have to do another show about
Yes.
weather. But what should people do, other than, what can we do in our everyday lives to produce less carbon dioxide?
Simplest thing that I think is on the horizon, Norway by 2025 will have no gasoline-powered cars. It'll be all electric.
Well, they're making it very easy for
What are they making
the
their electricity
Norwegians.
with?
Well, the electricity is made with coal, but it's being made in Norway it isn't. It's being made by wind almost entirely, but if you've ever been there, it's always windy. Here we don't have always windy, so we're using much more efficient means. The comparison I like is that if you drive an electric car, it operates at the same cost as if gasoline were 60 cents a gallon. And so that's one way. We're calling it beneficial electrification. If you don't burn oil to heat your home, but instead use electricity, it's generated in much more efficient ways. Here locally, we get our power from Minn Kota, and Minn Kota is working really hard at carbon sequestration, which is to pump the carbon dioxide down into the Bakken Formation and use that for enhanced gas recovery, which then is being used to generate electricity in a much more clean manner than burning coal. And that's probably in our not too distant future.
Good stuff, Charlie. I wish we had more time, but we are out of time. So
I got all kinds of time, Todd. I'm retired.
And maybe someday I will be too.
Maybe I should be more efficient in my presentation. I'm sorry if I go long-winded.
That's okay, because that means we can, now we can have more presentations.
There you
so
go.
We'll schedule another show very soon, I hope.
Very good.
Charlie Parson, thanks for joining us.
You're welcome.